Hello everyone, this is Mohammad Abdulaziz, and today I'll be doing with you the sixth sheet for the functional data structures course. So let's get to it. So the first exercise, as you can see here, you're basically required to define a function that expresses the complexity of naive reverse. And what that means is you're required to define a function that counts the number of calls to cons, basically. So let me show you what that means. So, for example, the complexity of I'll just say let's say we have a function. Let's say we have a function fun. Okay, function f, for example, and that function is defined in the following way. So it takes a natural number and just returns a list in the following way. So if you take a 0, then you return an empty list. If it takes a successor of a natural number, you return so it returns to you a list of units. Okay. So if you take a suc n, you return this list. So end f of n. Okay. So for instance, like with this measure of complexity that we want to do for reverse, but if we apply it to this function fun, the complexity of fun. Okay. So we want to define a function c fun. Okay. So the complexity of f. So we're defining a function cf. Okay, where again it takes the same arguments as f. Okay. But returns the number of cons that have been that f would the number of applications of cons that f would do given this argument. So here, for example, cf of 0 is 0, and cf of suc n will be equal to 1 plus and cf of n. Okay, so we want to come up with a function like that, but for the reverse function. Okay, so here, as you can see here, the reverse function, what it does is that it doesn't really call cons itself, but it calls append. And the function append is the one that actually does call cons. Okay, so and we want to count the number of calls to cons here. Okay, so let me just write down that function reverse. Okay, so now let us look into the definition of append to see how many calls to cons append does. Okay, so here in the empty case we call nothing, and in the cons case we call cons once. Okay, so if we want to devise a function that computes the number of calls to cons that reverse does, we do it in the way I just did on the paper there. So t reverse, so you have a function that takes the same arguments as reverse, but it returns a natural number instead that counts. Sorry, this should be actually, we're starting with append here. Okay, so we will want to return the number of calls to cons that append would perform for an argument for this argument. Okay, so if that list is empty, then the append calls no cons, and if the list is not empty, append calls cons once, and then you will recursively call the append again because. Okay. So append actually should be taking 2 arguments, but since the recursion is done on the first argument, it doesn't. Wise. So let me just make sure that the recursion is on the first one. So append. Yes, it's on the first one. No, but let me just. Yeah, that's the right one. Okay. So here, that's basically that's the number of. This is our estimate of the complexity of the append function. Okay. So let me just note something. So when I say the complexity of something, you really define what operations do you want to count and consider the complexity of a certain function. Here in this case we're counting cons, for example, but in some other cases, as you'll see in the homework, you count other operations like comparison operations, for instance. Okay, so now we have that, and I want to define the number of cons that reverse does when it's given this argument. So t reverse here. So what should that be? So that should be t reverse of x's plus so t plus t append of with the first argument x's with the first argument that one, and the second argument that second one. Okay. So t append reverse of x's, and the second argument should be the x plus t reverse of x's. Okay, so there's a mistake there. Yeah, we need to make sure that this actually returns a natural number. So this should be list, another list, and gives you back a natural number. Okay, so what is there? Oh, 0. Okay. So now we have the function, that function, okay? We know that this function is going to be quadratic in the length of the argument, in the length of the given list. But we don't know exactly the expression because we don't want just an upper bound on the number of calls of cons, but we want an actual an exact estimate of it. So we need to find that estimate first, and the way you would do that, this is not a formal thing, but the way you would do that is by simply calling this t reverse for different argument for different lists of different lengths, and then see how that sequence evolves. So you can just do this. So t reverse, let's say an empty list, so it's 0, and then a list of one member. Yeah, because we don't call cons at all here. And then a list of two members. So one call cons and a list of three members. Okay. So in any case, we want to know what is the progression of that. So like a good way to do that is to see it as a list, to return a list of natural numbers, and that list represents a sequence that shows the growth of this function. So the way you can, so firstly, if you want to build a list, if you given a natural number, if you want, so you can do this. So let's say I want to build a list with three members, a list of zeros that has three members. So we can do it. There's a function in Isabelle called replicate. So let's see what the type of it is. So it takes the number, which is the length of the list, and then the member, and then the element that you want to repeat or replicate as many times as n, and it gives you everything back. Okay, so we replicate for instance 0. Okay, so this should give us a list of 4 zeros. Okay, and since we don't really care about the value, actually, we can just set this to unit. So whatever. So it's a list of 4 elements, okay? And then what we can do here, okay, so we might want to try this first. So we want the number of calls to cons that replicate will do if you're list of 4 members. Now we want to do that for 0, 1, 2, 3, etc. So that we can try and guess the pattern actually. So what we can do here is that we can quite simply so here I will just map this function on a list that has natural numbers. Okay, so here, and then this will give us another list okay, and this will give us another list of the number of calls to cons that we are that happen by calling this function inverse. Okay. So so the way you try and come up with that function is by, the way I do it is by trial and error basically. So here we have 0, 0, if you, so we have 0, 0, 1, 3, 6, 10, 15, okay? That comes from 0, 1, 2, 3, 4, 5. So if I consider these numbers there, the input as n, I want to come up with an expression in terms of n that corresponds to this output list there. So if we know that it's quadratic from the question, so let's say it's just n squared. That doesn't work because 1 should be 1 also. So I would say, for instance, n times n minus 1. That's also quadratic, and that will satisfy like n times n minus 1 times 0 equals 0, and times 0 times 0 minus 1 is going to be 0 because here we're dealing with natural numbers, so that will evaluate to 0 when we're when n is equal to 0, and when n is equal to 1, so for n equals 0, and also it will be equal to 0 for n equals 1, because that thing will still be 0, and for n equals 2, that will be 2 times 1, so here we have 2, but that's 1. And for n equals 3, that expression there will be 3 times 2, which is 6. So actually it could be n times n minus 1 over 2, so 0, 0, this would be 1, and this would be 3, so that seems to match the list. So, and then we try it with 4, so it's going to be 4 times 3, which is 12 over 2, that is 6, so that makes sense. With 5, 10, so yeah. So it seems like this is the expression that we want, n times n minus 1 over 2, okay? So what we want to prove is that the naive expression, the reverse implementation of reverse calls cons this number of times. Okay, so the length of the given list multiplied by the length of that given list minus 1, all divided by 2. Just make sure that this is written correctly. Yeah. So now, okay. So now we prove that by induction and access. Let's try that. So here, by sim, okay, that works. And let's see what's going on there. So that probably will not work. Let's just try it. Probably will need a list and a chain of equalities. Okay, so the way we start that is by firstly using the induction hypothesis. I will write that thing using the induction hypothesis. Okay, so T reverse of x and x's just will be that. Okay, a and x's, sorry. So hence for that, what so this should be an a, and the left hand side is the append of a and x's. So taking reverse instead of an a, T reverse, sorry, that's not taking. So T reverse of the equals axis, which is the left hand side. Okay, sim. We can also just get that out of there. Okay, so that's the induction hypothesis. We're using the induction hypothesis to the right now, and what we want to get that. So let us just simplify that right hand side as much as possible to see what what a simpler version of what we want to get. So I would do the following. This is just for testing. Sorry, this is just not for testing. This is just for simplifying the right hand side to make it into something a bit more readable. So I'll just say equals 0 by auto, for instance, and then you see, okay, so the right hand side is actually just that expression. So that's our goal, okay? So, so we want to get from there to that thing, okay? So that's that, and then t reverse. So t append of reverse of x's and a will be so t append of reverse of x's. So we should prove a lemma that this thing is actually equal to the length of x's. So this thing equals length of x's, should be true. It says apply auto. So that did not work. Okay, so let's just do it for that. Yeah, okay, and then okay. So that's number one. And we also need to prove that the length of the reverse of a list is the same as the length of that given list. So I think this is already in the same set. So now what? So let's look into that. So find theorem's length of reverse of a given list. Yeah, that should be it. Let's see if that will work. If we like that here. Okay, so we already have that. So t append of something equals that. Yeah, so t append of that, it should just be x's like that. Okay, so let's see. Yeah, length of reverse of x's. So I can just use that number that I found there. Length of so it's not working. Oh, of course, because that reverse, this lemma that I found there is not for the reverse that we implemented there, so we actually need to have an equivalent lemma for our own reverse. So this is just rev. This is the standard reverse in the library, not our reverse. So length of reverse of x's equals the length of x's. So let's see now how it looks like. So it works. Okay. Now next, yeah, as we said, we want to get this thing up there to that shape. So what I would do is first I will try and get that length of x's in the numerator of that fraction there, because this actually, the parentheses are like that. Okay, so we want to get this into the, so I can say also that right hand side equals t times length of x's plus whatever we have there. So let's see. Okay, so we can get it inside. So let's be more aggressive and try to do something more than just getting it inside the numerator. Okay, so we also want to get, we would like to get this 2 inside that fraction there, and then have the 2 minus 1 equals 1, and then we will have our we will have that expression that we want. Okay, so here what I'm basically going to do is so the reason I'm not doing this on paper because it looks too simple to me to be done on paper, but yeah. So anyway, so that should be +2 like that. Okay, so this also worked. So now what we want to do is to basically have 2, just bring this 2 there, so before the 1. So what we basically need to do is to transform this length minus 1 plus 2 into a length plus 1, and then you have the right hand side down there. So I think this will not work because we need 2 cases on x's. We need to basically make sure that this x's that the length of this x's is greater than or equal to 1 in order for you to be able to bring the 2 there, because we have a lemma there, because these are natural numbers and you cannot easily subtract natural numbers, unfortunately, but let me just show you. So here we have some natural number minus another natural number. Okay. Okay, and then I want to add another natural number to that. So that is basically the lemma that we are looking for. That is it. And the associativity. And as you can see, you need the j to be greater than or equal to the k, so that you don't have a situation where you have 0 minus 1 equals 0, for instance. Okay. And so that's what we can do here in this proof is to do the following. To split this into 2 cases where the length of x's is not greater than 1, greater than or equal to 1, and the proof will also work in this case because if it's not greater than or equal to 1, then it's less than 1, which means that it will be 0. So the whole thing will be 0, and the right hands that side will be 0, and that side will also be 0. And in the other case, if it is greater than or equal to 1, then we'll have our equality. Okay. So let me just write that. So here we want to change this into a +1. Okay. Now of course that will not work because we need this precondition first. So what I would do here is to just split the proof on the cases of x's and see. Okay, so it doesn't work. Okay, so let's just go slower with that. Maybe so what's the name of the lemma then? So we'll just this time and so yeah, it does it because okay. So the problem is that simp is applied only to the first case. And since I've split this into 2 cases, we have case when x is empty, the empty list, and the other case when x is the cons list. So this is splitting cases on the data type, if you remember from 1 week ago. Okay. So now that we have that, we can just say primary showcase, okay, because that is quite easily shown to be distributed. Okay, so that proves our lemma. And now let us go to the second question. So here we have stability of insertions, or so the question says, okay, take a look into the function, the result implementation of sorting, sort key. Okay, so let's do that. So we can just sort key and then Control C and go there. Okay. So it seems like it does fold this function that does insort key. Okay, and insort key is a function that is shown here. It so firstly you have, okay, so let me just go back for 1 moment. So this sort key basically is a function that sorts the list x's, but not based on the ordering relationships between the numbers of x's. No, it is based on x's is a list of keys, and you want to sort those keys based on the relative ordering of the corresponding values. And f is a function that maps a key to its value. Okay, so let me just quickly show you on the paper what I mean by that. So, for instance, you have, so f maps 0 to something. I'll just show you that. So f maps 0 to something, and say it's just defined on 0, 1, and 2. Okay, so I will say does that. So 2, 3, 1. Okay, so it maps 0 to 1, 1 to 3, 2 to 1. This is the key and this is the value. Okay, and then you want to sort a list of keys based on those values. So if I'm given the list of this list of keys, I want it to be sorted in what is it, ascending or descending order there. Ascending order. So here I want these keys to be sorted based on their corresponding values. So the corresponding values, if they are sorted in ascending order, it will be 1, 2, 3, and 1 here will just give me the key number 2, and 2 will give me the key number 0, and that's it. Okay? So that is the kind of sorting that we're having. We're sorting keys based on the corresponding values. So what we want to do is to show that the stability of that function, of that sorting function. And what that means is basically if you have two keys of the same with the same corresponding value, then they should not be removed. So if we, for example, here had 2 also mapped to so what is it, 0, 1, so let's say that both of those have let's say that all of those were mapping to the same value, then in this case you would return exactly the same list. Okay, even though that list is also valid, valid sorting because all of them are the same value, but that's not stable. While that one is stable. Okay, the reason I'm saying that is because here, although this is a sorted list, like this list of keys is sorted with respect to the values, the ordering of list of keys was changed basically unnecessarily. Well, this one is stable because it's sorted, and keys with the same corresponding value have the same order in the list. Okay. So let us try and state that lemma that indicates that the sorting function is stable. Okay. Now we'll just simply copy it from there. Okay. So, yep. Okay, so we want to prove that. So there is a lemma already in the library that proves this, but we want to do it ourselves. So let's do induction on access, and then try auto and see what turns out. Okay, so here we want. Okay, so the induction hypothesis is that, and the conclusion is that, and what we want to basically do is to get this this entire thing to be before the filter. Okay, so basically we need to see lemmas that can get this filtering past this insert key. So let's look for lemmas that talk about that. So that's what I do. So what we want filter and insert key. So this function, okay, so I actually forgot to show you what that function is about. I tell you. So that function is works in the following way. It just inserts a given key X into a list of keys in such a way that the output list of keys is sorted according to the corresponding values. Okay, so that's why you compare the value of the current key with the value of the head of the list, and you keep doing that until they have and as long as you're strictly greater than as long as the value of f of x is strictly greater than f of y, you will keep moving x forward in the list. Okay. So we want lemmas that relate that. So it seems like, okay, so we have here two cases that relate filter and sort. Okay. So the first case. Okay, so we have here two cases also in the proof actually. So the first case is when a is the same as the value of corresponds to the key AA, which means that that a like this that AA, which is what we want to insert, satisfies the predicate of the filtering, and that is this case because you have p of x, okay, and then you're trying to insert x, okay. But another precondition of that lemma is that mapping of the key function on the list of keys would give us a sorted list, and what that is, this is a predicate that says that a list of values is sorted, not a list of keys is sorted. So that's why we're mapping f of x on x. Okay, so in order for us to apply this lemma that will fit our first case there, we need two preconditions. The first one is that, and we already have that because AA is the same as that one. Okay, and the second condition there is that the output is sorted. Okay, so let's see how would that apply there. We want to make sure that this is sorted, okay, and we should have a lemma already that says that this is that sort key of k and x's is sorted. Let's look for that lemma. So find theorem sorted and sort key. Is that it? Yeah, that's what we want exactly. Okay. So we're going to use this lemma and the second lemma. Get a founder to discharge to manipulate the first of all. So actually, it seems like this other lemma here is already somehow in the sim set. That's why that's why this lemma already worked. Let's try it. Yeah, it's already in the sim set there. So, and now what we want to do is so we have this there, filtering of x's. Okay, so that induction hypothesis was applied. And all what we need to do now is to say that in sort key AA equals AA like that. And the way we need another lemma for that to work. Let us just try and look what we're searching for. So we basically want some lemma of the form in sort key and something from something else. We basically want we want that lemma. So I will actually just add it there and see if it rewrites, otherwise I will investigate its precondition. Okay? So here it works and it removes our first subtotal. But let's see why the first condition actually. So the first condition here is that A is less than or equal than f of A, is less than or equal to f of anything in x's. Okay. So why does that apply here? So we want f of k of double A to be less than or equal than k of anything in x's. Yeah, and that is the case. Yeah, that is the case because simply what we have when we apply this filtering, when we apply this filtering, we only have members in x's whose we only have keys in x's whose values are exactly equal to the value of corresponding to double A. Okay, and that means that every member in that list has the same value that has a value that's less than or equal to the value of A. In particular, this should follow from that lemma. Find theorems, filter. So we want to say filter, and we want to we basically want to say that we want to find a lemma that talks about members of the resulting list from filtering another list based on a predicate. So everything in that set. Let's see if that's exactly what we want. Yeah, it's the set of filter. Okay, so filter takes two arguments and we want numbers in it. And we want some. Okay, so let's just be more explicit there to make it clear. Filter P. And then P X. Okay, so why is that precondition holding if we don't have that letter there? Okay, so let me just try and get that. Another way to do that is to just try and do this as a lemma. Okay, filter so for x in set of that we have that k of x equals, let's say, k of y. And see, because now which so that's not Oh, sorry. Equal. So auto solve should give us a lemma that does that. Sledgehammer. Yeah, so it seems like there's something in simp there that can prove that, but I can't find it actually right now. Just try and do it that way. By simp, but let's see if. Yeah, so we have this lemma somehow in the simp set, but I don't really know what its name. So anyway, because we have a lemma that allows us to prove that. We have a lemma basically that says what I just wrote there. We know that the result of this filter is going to be is a list of keys whose corresponding values are all equal to the corresponding value of AA. Okay? So that's it. So what's the lemma again? Okay. And now the second case is when double A doesn't satisfy that predicate. I think we had it already somewhere there, so we have to go to filter and insert or what is it called? Filter and insert key. Yeah, so it's this case. So that's it. So that's it for today. I hope you enjoyed it, and if you have any questions, please post them on the Piazza forum. Thanks.